Hi, so welcome to our latest video on trig. We're going to be talking about a lot of trig formulas today, including the sum and difference formulas. So if you remember last video, we got exposure to our first and most important trig identity, sine squared plus cosine squared equals 1, or the Pythagorean identity. And we're going to see a lot more today. It's going to seem a little bit overwhelming at first, actually, but what I want to show you, the most important thing, I think, is that from a couple of these formulas, it's very easy to get the others. And in fact, I think that cutting down on memorization is going to be really important. So where do we start? So first I want to see, we can see from the definition of sine and cosine that they don't behave very well under addition or subtraction, right? So I think maybe early on you might have made the mistake of looking at something like sine of the sum of two angles, and then maybe like thinking that you could break that up and write it as the sum of the sine of the first angle plus sine of the second angle, right? But that is definitely not true, and it's not true when you think about what's going on the unit circle and the fact that sine and cosine are x and y coordinates. So it's actually kind of remarkable that there are formulas at all that allow us to compute sine of a sum or cosine of a sum. But these formulas do exist. And before we get into them, I want to say a little bit about why this is a useful idea. We're kind of leaving the realm of immediate applications. When we were looking at sinusoidal functions, we could see that we were going to model lots of stuff with sine and cosine. But now we're kind of getting a little bit more into the algebra and some of the abstract math. And I just want to say a little bit about where we're going with that. So one, we're going to be using these formulas to compute more exact values of the trig functions. So right now we only have the special values, those like 12 points on the unit circle, where we know the values exactly from geometry. And we might want more. Or really, we might want to know how our computer or our calculator is finding more of these values. And it has to do with these formulas we're going to talk about today. Secondly, we're also going to be using these formulas to derive a lot of other ones. And in general, we're going to start to be able to solve equations that have trig functions in them and that could be quite complicated. And like the third reason, maybe the most important reason, is that next year these sum and difference formulas are going to be really important for learning how to take derivatives of functions like these, like trig functions. So we're not going to see that this year, of course, but that's where some of this stuff is going. Okay, so let's get into it. So the most important formulas we're going to see today are these that are on the screen right now. Okay, so just the background of the notation. Alpha and beta are these symbols that you see here that look like A and B, but they're Greek letters, right? And no surprise, they're the Greek letters A and B, and we're going to be using them for angles just like we use theta for angles. So typically you use alpha and beta if you just happen to have two angles instead of one. So sine of the sum of two angles can be broken down into sine and cosine of each angle, but in this weird way, right? So to read this off, sine of alpha plus beta equals sine of alpha times cosine of beta plus sine of beta times cosine of alpha. So notice that the two terms in this sum are kind of alternating. So I think of it as sine of a sum equals sine cosine plus sine cosine, and then I just remember to swap the alpha and the beta in the second term. Okay, so this is very memorizable. The second one is about cosine, and you can see that instead of sine, cosine, sine, cosine, now we have cosine, cosine, sine, sine, and instead of a plus, there's a minus. So two things have changed between the sine formula and the cosine formula. Yeah, that makes the cosine formula a little harder to remember, but you're going to want to remember this one as well. So these formulas are complicated enough that I don't want to take time in this video to explain why they're true. I'd like to talk about it in class. It follows from a bunch of stuff in geometry, so it's not incredibly complicated. I just don't want to take that time. But everything else in this video is actually going to follow from these two formulas. Okay, but before we get to that, let's give an example of how you could use this right off the bat. Let's say we want to compute sine of 11 pi over 12. All right, now 11 pi over 12, you could think about where that's going to be on the unit circle, but it's not going to be one of our special values. So because it's not one of our special values, we need to do a little bit of work to find it. Okay, so I've written out the calculation here. It starts by realizing something about 11 pi over 12, realizing that we can break it down into the sum of two values that we already know. So 11 pi over 12 equals 8 pi over 12 plus 3 pi over 12. Okay, and 8 pi over 12 I can simplify to 2 pi over 3. And 3 pi over 12 I can simplify to pi over 4. Okay, let's pause for a second. How on earth would I have known that if I was just being given 11 pi over 12? Well, I wouldn't. I had to make a little bit of a guess, right? But if I know that I'm going to be using the sine sum formula, then I'm looking for a way to break up 11 pi over 12 as a sum of things that I already know. Otherwise, I'm just not going to get very far, right? So maybe I searched around a little bit until I realized that I could get it to be 2 pi over 3 plus pi over 4. All right, now it's really just plug and chug. So first, I write out the formula, and I replace the alpha and the beta in the formula with 2 pi over 3 and pi over 4. So I'm just making sure I have the formula correct and everything substituted in correctly. But these are all special values, so I can get out my unit circle, or I could draw myself a unit circle, and I could find the coordinates of the points I'm looking at, pi over 4 and 2 pi over 3, and then really just substitute everything that I know, right? Sine of 2 pi over 3 is the y coordinate here. That's root 3 over 2. Cosine of pi over 4 is the x coordinate of this point. That's root 2 over 2, and so on. I keep making that substitution, and then the rest is just simplification, right? So I do a little bit of fraction stuff. I know some properties of square roots. I know that if I'm multiplying two square roots together, I can combine those and multiply the things inside the square root. And so I get square root of 3 times 2, or 6, over 2 times 2, which is 4. And then, plus, well, this minus here can come outside of the product and then turn this plus into a minus, and then I just have root 2 over 2 times 2 is 4. Those fractions have the same denominator. That's kind of nice. So I could even bring those last things together. Okay, so really, once you remember the formulas, this is about substitution and using what we know about the unit circle. Okay, so the other thing about the sum formulas is that we can use them to get lots of other formulas as well. So you might have wondered if there's something for a difference. If I, instead of having alpha plus beta, I have alpha minus beta. Well, of course there is, but in fact, I can derive it from the last formulas. Okay, so make sure you have the sum formulas in your notes, because what I'm going to ask you to do is to pause the video and see if you can find these formulas on your own. And I'm going to give you a series of hints that might lead you there, but if you already think you might know what to do, then you can pause it right now. So the first hint is that if we're looking at, say, sine of alpha minus beta, well, a subtraction is the same thing as adding a negative, right? So I could rewrite this alpha minus beta as alpha plus negative b, or minus b. Same thing with cosine, right? So if I have it as a sum, that means I can use the sum formulas. All I have to do is substitute minus beta for beta. Right? Well, once I have that substitution, then I can simplify it further by remembering my properties of cosine and sine. Specifically, that cosine is an even function, so when I make the input negative, nothing happens, and sine is an odd function, where if I make the input negative, the sign of the output flips as well. So we've talked about odd and even functions before. Now we're starting to make use of that in our formulas. Okay, so if you think you know what's going on, if you think you might know how this goes, then I actually think it's a really good idea to pause and figure this out for yourself, because it means that now you know you don't need to memorize this. But if you want to know the answer, here it is. So in fact, really the formulas look very similar to the last ones, but what you notice is that like where there was a plus before, now there's a minus, and where there's a minus before, now there's a plus. So is this really that hard to memorize from the previous one? Probably not, but it's going to get worse, and so being able to do these little derivations, you will help yourself out so much. I can't emphasize that enough. Okay, let's take a look at the last formulas for today. These are called the double angle formulas. So this is what happens when you want to take sine of twice an angle or cosine of twice an angle. And again, you know something about sine or cosine for the original angle. All right, so once again, there's formulas for this, for sine of 2 theta and for cosine of 2 theta. And you can derive these from the sum formulas. Okay, and again, like before, I want to give you the opportunity to pause and see if you can derive these. But your first hint is that sine of 2 theta, well, 2 theta is theta plus theta. I mean, we're back in elementary school right now, right? So, so why don't you write that 2 theta as that way, theta plus theta. And then, well, you can now use the sum formula again. But this time, alpha and beta are the same. They're both equal to theta. So you're just plugging in alpha equals theta, beta equals theta, and then see what simplifies. See if you can simplify what remains. Okay, so I've given you the chance to pause. Here are the final results. So, like I said, plug theta in for both alpha and beta. Now we get the same term twice, right? There's no difference between these terms anymore, because when I swap alpha and or theta and theta, I get theta and theta. I'm sounding very silly right now. So if I have the same term twice, then I can just combine those and say 2 times sine theta cosine theta. So that's kind of nice. The double angle formula for cosine is only slightly less nice. I get cosine cosine minus sine sine, right? That was our original sum formula. And this time I can combine the cosines and the sines, because again, they're the same thing. So I get cosine squared of theta minus sine squared of theta. All right, now that's already pretty useful. But I could actually take this last formula and go even further. And the trick for doing that is remembering our old friend, the sine squared plus cosine squared equals 1. Okay, like I said, this sine squared plus cosine squared equals 1 is really the most useful trig identity. It shows up all over the place. And right here, whenever you see that a sine or cosine is being squared, that sine squared plus cosine squared equals 1 should pop in your mind. It's like, this might be a useful thing to use right now, because chances are it is. So what we're going to do with this is we're going to take this last part of the formula and do a couple substitutions. So the first thing that's going to happen is that we can take this cosine squared and rewrite it as 1 minus sine squared using this formula, right? And just rearranging it to get cosine squared by itself. So that means subtracting sine squared. So if I make a substitution, cosine squared equals 1 minus sine squared, and just right now it's in parentheses, but then now I've got the same thing twice, so now I can write this as 1 minus 2 sine squared theta. That's nice, because it means to find cosine of 2 theta, I only have to know sine of theta, and I can plug it in from that. But if we could substitute in for cosine squared, we could also have substituted in for sine squared. So in the next one, we're going to do the same thing, but backwards. We're going to take the sine squared and write it as 1 minus cosine squared. So now here we have a minus minus. So when we distribute that, it's going to turn this minus into a plus. And then I can combine it with the other cosine squared to make 2 cosine squared minus 1. All right, so already we're getting past what I think you could reasonably memorize all of, unless you're really, really good at memorizing. I certainly, in my experience as a mathematician, I've only ever really needed to memorize the sum formulas. Like I said, you can use them to get everything else, and I do frequently. With the last thing I want to do, so here's the homework for today. A couple things. The first problem, you're going to be using the difference formula to find sine of pi over 12. Again, pi over 12 is not one of our special values, but pi over 12 is equal to pi over 4 minus pi over 6. And if you don't believe me, that's just a little bit of fraction arithmetic, which you can do. So what am I asking you to do right now? I'm asking you to use the difference formula from the third slide and plug in alpha equals pi over 4 and beta equals pi over 6. Substitute everything in. Use the unit circle to plug in those special values, and then simplify as much as you can, just like I did on the first slide when I computed sine of 11 pi over 12. Here's the second problem. So our last formula, if I combine it all together, was cosine of 2 theta equals 2 cosine squared minus 1. We could use that to find cosine of pi over 8, but in a slightly reversed way. Here's what's going on. So if theta is pi over 8, then 2 theta is pi over 4, which means 2 theta is now one of our special values. So what I'd like you to do is plug theta equals pi over 8 into this formula, and then use what you know from the unit circle and get cosine of theta by itself, meaning you have to do a little bit of algebra, and you'll be able to solve for cosine of pi over 8 without a calculator. It'll not look nice, and in fact, I can tell you now that it's going to have a square root with another square root inside it, but it will be an exact value for cosine of pi over 8. Okay, as always, we'll make sure we can do these problems. Both of these problems are very important, and we'll make sure that we can all do them in class. And I'll see you then. So have a great rest of your evening or morning.